This is our third video lecture for the probability graduate level class. Last time we ended with a fact that resulted from conditional probability definition, and today I want to extend that fact. So let's recall the fact that I was talking about. The fact that we had was the probability of A intersect B is equal to the probability of A given B times the probability of B. And this stems from the definition of conditional probability, where B, the probability of B is greater than 0. An extension of this result is called the multiplication rule. Some people call it the multiplication rule. It's an extension above that. And here's what it says. It says, given events E1, E2, all the way up to En, then the probability of E1 intersect E2, intersect E3, intersect, keep going to the intersection of En is equal to, here's the result, is the probability of E1 times the probability of E2 given E1 times the probability of E3 given E2 intersect, or I'll say E1 intersect E2 times, and keep going. And the last multiplication that's involved here is times the probability of En given E1 intersect E2 intersect all the way up to En minus 1. The proof is easy if we know where to start. And what we'll start is that the right-hand side of this equation, so what we'll note is the probability of E1 times the probability of E2 given E1 times the probability of E3 given E1 intersect E2 times the probability of En given E1 intersect E2 intersect all the way up to E sub n minus 1. What that's equal to well, it's the probability of E1, that's the first thing involved, times the probability of E2 given E1 is nothing more than the probability of E2 intersect E1, which I'll rewrite as E1 intersect E2, over, it would be the probability of E1, times, now we need to multiply by the probability of E3 given E1 intersect E2. But I'll say that's the probability of E1 intersect E2 intersect E3 over the probability of E1 intersect E2, and we keep going until the last conditional probability here can be rewritten as probability of E1 intersect E2 intersect all the way up to the intersection of E sub n minus 1 intersect E sub n all over the probability of E1 intersect E2, intersect all the way up to the intersection of E sub n minus 1. And that's based on the definition of conditional probabilities from the previous step, scientific step. And what you notice is that the probability of E1 and the probability of E1 in the denominator and the numerator here will cancel with each other, so that just leaves this probability. But that's listed here in the denominator, so they cancel. And you keep having cancelizations until all you're left with is this guy right here. And that's what we were trying to prove. So that's the proof. Let's look at an example. So let's go back to that urn problem. So an urn has 8 white balls and 3 red balls. Then we're going to say 3 balls are chosen at random. Without replacement. One after another. And the question is, find the probability that the first ball is red, comma, this comma means and the second ball is white, comma, so and, the third ball is white. Okay, so that's our problem, and we're going to do it by this multiplication rule. Okay, so the probability that the first is red and second is white and third is white is equal to, by the multiplication rule, is the probability that the first is red times the probability that the second is white given first is red, that's conditional probability, times the probability that the third is white given first is red and second is white. Okay. So the probability that the first is red, let's remember our urn has 8 white balls and 3 red balls. So you're choosing a ball, the probability that it's red is 3 out of 11. That's what we have. So you could multiply that by, we're saying we're choosing 3 balls, and so then you have 10, and then 10 balls left, you can choose any 10, and then there are 9 balls here. You can write it this way if you like. And then to choose 3 balls, there's 11 ways to choose first ball. Then for each one of these 11, there's 10 ways to choose the second ball, and then 9. But that just ends up being 3 out of 11, okay? Times. Now this is a conditional probability in which we're asked to find what happens next, given what happens previously, and we just can put ourselves in that position and calculate this pretty quickly. So I'm saying, okay, what's the chance that the second ball is white given the first is red? Well, remember there were 8 white and 3 red, so we know the first one is red, so that leaves 8 white and 2 red. So the chance that the second is white is 8 out of 10. And then times the chance that the third is white, given that the first was red and the second was white. Well, that means that we now have 9 balls, 7 of which are white. So we get 7 out of 9 here. So this is equal to, if you don't mind, it's 3 out of 11 times 8 out of 10 times 7 out of 9. And that's our answer. Well, we've been talking about conditional probability. And sometimes word problems are written that are conditional probability problems. And we need to know wording that indicates conditional probability. So here, let me say the following. So as a comment, the wording the percentage of A that is B means, or indicates, that you're finding the probability of B given A. That's what that indicates. Okay. You know, we were in this previous, let me say something here first. We're going to use this comment of understanding how a word problem can indicate a conditional probability in a few minutes. But before I get to that, I want to go back to something here. I had said in the last lecture, and we used it here, that it's not so hard, because of reduced sample space when everything's equally likely, to compute a conditional probability of what happens next given what happened previously. But the other direction can be hard, except we have a fact that helps us with that type of calculation. That fact is called Bayes' theorem, and that's what I want to talk about next. So here's Bayes' theorem. It says let A and B be two events where the probability of A is greater than 0 and the probability of B. Okay. Then the probability of B given A is equal to the probability of A given B times the probability of B over, it's a long over, the probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. So this is Bayes' theorem, and you'll notice Bayes' theorem allows us to switch the order of the given and what's asked for, but it requires something a little bit more too. Well, I would like to prove this to you. Okay, so we'll start over here on the left-hand side with the probability of B given A. By definition, that's the probability of B intersect A all over the probability of A. Well, the probability of B intersect A can be thought of as the probability of A intersect B. And the probability of A, the way that I'm going to rewrite that, is I'm going to rewrite that as the probability of, well, A is the same thing. So probability of something that's equal to A. Okay, so what's A? A is the same thing as A intersect B union A intersect B complement. So B complement I've been doing with a prime here, and that means the things that aren't in B. And I'll talk a little bit more about that a little later in this lecture in a more general setting. But here's what we have. If you want to get A, you take what A has in common with B and what A has in common with what isn't in B. That gives you all of A. And it turns out these two guys will be mutually exclusive. So this is probability of A given B A intersect B is what I'll leave it as for right now, over, and the probability of a union of two mutually exclusive events is the probability of the first guy plus the probability of the second guy. Now, using the definition, or fact, I should say, we started this lecture, recall, the probability of A intersect B is the probability of A given B times the probability of B. And then here's the probability of A intersect B. I'll rewrite the probability of A given B times the probability of B plus the probability of A intersect B complement is the probability of A given B complement times the probability of B complement. And that's what we wanted to show. So I called it C here when I should have written B prime for B complement. Okay? Sometimes books and myself will denote B complement with B prime or B with a superscript C to represent the complement. Okay, so that is what I wanted to show. They match. I started with the left-hand side. And so that's the end of the proof. Let's look at an example involving that urn, the familiar problem with the urn. So, example, an urn has 8 white balls and 3 red balls. A ball is selected, 2 balls are selected one after the other without replacement. Find the probability, this is the conditional probability, that the first is white, given the second is red. Okay, this is a problem, this is a conditional probability problem, where we're asked to find a probability of what happened in the past, given what happened in the future, given what happened next. That's tougher. And so what we'd like to do is translate that. Okay, so let's translate that using switch what's given, what's asked for, using Bayes' theorem. So here, using Bayes' theorem, the probability of first white given second red would be equal to, okay, this is the probability that the second is red given the first is white. So that's just switching them, times the probability the first is white. Now, the fraction part of Bayes' theorem starts off the same way as the top does. So this is the probability that the second is red, given first is white, times the probability that the first is white, plus, is what Bayes' theorem says, plus what? Now, it's the probability the second is red, given the opposite of the given part over here. Well, the opposite of the first draw being white is that the first ball was red, times the probability the first is red. Common. Okay. We'll come over here and make those computations. So to make these computations, we have the probability I'm looking at that the second is red given the first is white. So I'll put myself in that position. First was white. That means we have 7 white balls left and 3 reds. So that means it's 3 out of 10 times the probability that the first was white. That's 8 out of 11. All over, well, the second part starts the same way. It's 3 out of 10 times 8 out of 11. And then plus, now, we're working on the second is red given the first was red. So I put myself in that position. The first was red. So that means there's 2 red balls left out of 10. So it's 2 out of 10. And then the probability the first was red was 3 out of 11. So whatever that is the answer. Let me make sure that my previous work I got the same answer. Yes, I did. Yes, that's right. All right. Well, what I want to say next is that we can extend Bayes' theorem to where we have maybe several events involved. And to do that, I need to make a preliminary definition. So here's the definition. A sequence of events let's say E1, it's finite sequence, E2 up to En, is said to be mutually exclusive and exhaustive if 2 things happens. So the mutually exclusive, you know, is that if EI intersect EJ equals to the empty set when I is different than J, the exhaustive is new, and that's if E1, so both of these have to happen. E1 union E2 union, we'll keep union, up to En equals to the whole sample space S. So that's what it means to exhaust all of S, is that you can get all of S by unioning up E1 through En. Okay. That allows us to come up with something called the total law of probability, which I used in my proof of Bayes' theorem, but I didn't really say that that's what I was doing. And I did it in a kind of a less complicated case, very simple case. But here's what the total law of probability says. It says let E1, E2, up to En be a sequence of mutually exclusive and exhaustive events. And let A be an event. Then, the probability of A is equal to the probability of A intersect E1 plus the probability of A intersect E2 plus, and we keep going, the probability of A intersect EN. So I'm going to do the proof right here, but the way that I'm going to illustrate this proof, at least I'll do one line proof, is I'm going to look at a Venn diagram. So here's my sample space, the whole box of my the whole box of my sample space. And let's say this is A. If you want to get the probability of A, the worth of A, well, we got these other sets here that are events. Maybe this is E1. Maybe this right here is E2. This right here is E3. Then we got E4. And then E5. And we keep going. And then we'll say this is E sub n. If you want to figure out what the probability of A is, what you do is you take the part of A that's in common with E1, plus the part of A that's in common with E2, plus the part of A that's in common with E3. This part of A, which is what's in common with A and E4, E5, and so forth. And none of them overlap with each other because the E's, 1 through En, are mutually exclusive. So they don't overlap with each other. The E's, I, intersecting J are all, their intersections equal to the null set, or the empty set. So they're mutually exclusive. And so that makes A intersect with any one of them, with any two of them, be two mutually exclusive events as well. And so that's how you get the probability of A. Well, to write it down a little bit more formally, probability of A, so I won't go through all the set theory details, I'll just say, is equal to the probability of A union E1, A intersect E1, union A intersect E2, union A, well, we'll keep union until we get to A intersect En. Okay. So that's just describing what I had here for the Venn diagram. That really, this A intersect E1, union A intersect E2, union all the way up to A intersect En, that part is A. And so the probability of the same set should be the same. What we notice about each set in that union we're taking the probability of here is that they are disjoint. So the mutually exclusiveness of the E1 through En give us this result is equal to A. Okay? Because unions are equal to A. Now the mutually exclusive one give us the results that when I union them each up, that A intersect E1, A intersect E2 are all mutually exclusive as well. And so what we end up getting is the probability of a union is the sum of the probabilities. That's equal to the probability of A intersect E1 plus the probability of A intersect E2 plus the probability of A intersect En. And that's what we were trying to show. And so that concludes the proof. Very simple. Okay. I think I'm ready to list Bayes' theorem in the extended version. Bayes' theorem extended. So here's what it says. It says let E1, E2, all up to En be mutually exclusive and exhaustive events. Let A be an event. Then the probability of E1 given A is the same thing as the probability of A given E1 times the probability of E1 all over the probability of A given E1 times the probability of E1 plus the probability of A given E2 times the probability of E2 plus, we'll keep on adding till we get to the last term, which is the probability of A given En times the probability of En. Prove this, and then we'll do a short example. Well, it takes a little while to write up, but we'll do an example where we only have 3 events involved. Okay, so prove. Proof is real simple. So here, the probability of E1 given A is the same thing as by Bayes' theorem, the original Bayes' theorem. The probability of A given E1 over the probability of E1. Okay. So I have written this, opposingly to what I wanted to do. I made a mistake, okay? Just a second, I need to think about this. Yes. Yes, I've miswritten it. I'm sorry. We have to go back. Okay? So here, I've made a mistake. It's what's written is. So let's see. Hold it just a second. I need a second. Yeah, I've made a mistake here. I didn't make a mistake. The statement's fine. Sorry about that. I got confused. Okay, let's go back. Okay. Let's say this is the probability of A intersect E1 over the probability of that. Because that's what it is. Yes, I started to say we can do this by Bayes' theorem, the first result, but no. We just write this down based on the definition of conditional probability. Sorry, I got confused. The statement is written correctly. This is what it is. Okay. Now, the top can be rewritten as the probability of A given E1 times the probability of E1. And now at the bottom, I'll leave alone, just the probability of that. But because the E1 through ENs are mutually exhaustive and mutually exclusive and exhaustive sets, we can use the total law of probability for the probability of A. And so this is equal to the probability, the top stays the same, all over what the bottom becomes, by what we just did, was the probability of A given E1 times the probability of E1 plus the probability of A given E2 times the probability of E2 plus, and we can continue on in this fashion using the total law of probability. And then we have the probability of A given En times the probability. And that is what we wanted to show. That's its proof. Sorry, I got a little confused there for a minute. Okay, what I want to do next is do an example. And so the example is out of a textbook. It'll take a few minutes for me to write it up. And before I write it up, if you remember in Bayes' theorem, we have this type of bottom where there's only 2 terms involved. It's the probability of A given B times probability of B plus the probability of A given B complement times probability of B complement. regular Bayes theorem without the extension. But here, B and B complement, you'll notice, are mutually exclusive and exhaustive. And that's how it works. So here's the example I'm going to look at. It says a total of 46% of the voters in a certain city classify themselves as independents. Those are the independents. Whereas 30% classify themselves as liberal. Okay. Liberals, we got the independents, and now it turns out that 24% say they are conservatives. Okay, in a recent election, 35% of the independents (62% of the liberals and 58% of the conservatives voted. Okay. Voter was chosen at random. Okay, here's what we want to find. It says find the probability, find the probability that this voter was an independent. Well, I don't have very much room here to write down what the problem says symbolically, but I'm going to try in this corner. You know what? I'm not. I'm going to do it. Okay. So we'll go back and forth. I think I have room here to talk. Okay. So the very first thing I see is probably a total of 46% of the voters, people who can vote. The people who can vote are the ones that we're talking about. Okay? Not whether you voted or not, but just the general population is the voters. 46% of them are independent. So the probability of independent, that's 0.46. Likewise, the probability of liberal, that was equal to, so it's 0.3, that's what this says. And then the 24% were conservative. So I'll say probability of conservative is 0.24. Then let's go back to what it says over here. It says, in a recent election, 35% of the independents voted. Okay? So 35% of the independents voted. And if you remember, we had that wording to look at. And applying the wording for a conditional probability, 35% of A is B. That means the probability of B given A. So here, I'll rewrite that. 35% says of the independents voted. Okay? So that means probability of voting, given that you are independent, is 0.35. Likewise, probability that you voted, given, from that other information, that you're liberal, they're telling me is 0.62. So I'm using that wording to gain symbolic information about what they're telling me in the problem. And the probability of voted given conservative, that is 0.58. That's what they're telling me. And what did the problem ask me? Well, it said, well, we got this vote at random. And they said, what's the chance that they were independent? So the question is, it's fine, the probability of independent given that you're looking at a voter. What's the chance? So here, the information that's given to me doesn't match the conditional probability setup. Okay? And I need to switch it. And so the way that I can switch it is using Bayes' theorem. So here's what I'll say. Note, the probability of being independent given that they voted, well, that's the same thing as the probability that they voted given that they were independent, times the probability that they were independent. All over, well, it's going to be the probability that they voted given that they were independent, times the probability of independent, plus, if you think of the categories, there were only 3, and they were disjoint, so mutually exclusive, and they were exhaustive. If you add up their probabilities, you see that you get 100%, okay? So here, they're exhaustive. So I'm using Bayes' theorem here with the exclusive, mutually exclusive, and exhaustive sets being C, L, and I, independent, liberal, and conservative. And so here at the bottom, I got the probability that you're voted given that you were liberal, times the probability of liberal, plus the probability that you voted given conservative, times the probability that you're conservative. And so these are numbers that we have, so I can just plug them in. So the first point is, the first part is 0.35 times the probability of being independent was 0.46. All over, here, this again is the same, 0.35 times 0.46 plus voter given liberals 0.62 times liberals 0.3. And then finally, the probability that you voted given conservative is 0.58. And you have to multiply that by the chance of being conservative, and that's 0.24. And whatever that numerical value is, that's the answer. Okay. That's an example of extended Bayes theorem. Next thing I want to do is give the definition of independence. Two independences. So here, we're going to say, let A and B be two events. We say A and B are independent if the probability of A intersects B is the same thing as the probability of A times the probability of B. Let's look at a fact, and then we'll do an example. As a fact, it says if the probability of B is greater than 0, or non-zero, and A and B are independent, then the probability of A given B is equal to the probability of A. So we think of independence really meaning that, in some sense, meaning the probability, if A and B are independent, what that means is if you know one of them happened, it doesn't affect the chance of the other one happening. Okay. So here's a proof of this fact. So note the probability of A given B, by definition, is the probability of A intersect B over the probability of B. And we're assuming that A and B are independent. And so the definition of independence gives me that this is equal to the probability of A times the probability of B over the probability of B. And the probabilities of B's cancel with each other, and I'm just looking at the probability of A. That's that proof. Let's look at an example. Well, before I do an example, I'm sorry, I'm going to do one more definition. Very simple definition. Given two events, A and B, then A and B are dependent events. If A and B are not independent events. Let's look at two examples. We'll conclude with that. Okay, so the first example is that a coin is tossed and a die is rolled. Let A be the event that heads occur, and B be the event B, it's obviously right, B equals the event that a 3 occurred. Are A and B independent or not? Or dependent events? That's the question. We use this definition to determine. And that's what we do in mathematics. We've got these facts, these definitions, these verifiable means to determine something. These definitions, they're just wonderful. We don't have to guess. We can figure it out.
So here, let's look at the sample space real quick. So let's recall that we flipped a coin and rolled a dice. And so our outcomes there are 12. There could be heads 1, heads 2. We could have gotten a heads then a 3 on the dice roll. Heads then a 4. Heads then a 5. Heads then a 6. Or we could have got tails then 1. Tails then 2. A tails then a 3. A tails then a 4. A tails then a 5. And finally, we could have gotten a tails and a 6. And that's the sample space. Okay, so the probability to compute, to determine, I should say, if these two events are independent or not, we need to find the probability of A, the probability of B, the probability of the intersection. The probability of the intersection is the probability that the heads and a 3 occur. Well, that's, in our sample space, everything is equally likely. And the number of ways that a heads and a 3 occurred was right here, one way, out of, there are 12 in the sample space. The probability of A is equal to the probability of the heads. And that was equal to 6 out of 12, which is 1/2. The probability of B, that's equal to the probability of the 3 occurring. And the way the 3 occurs is twice out of 12, so that's 1/6. So here, since the probability of A intersect B equals to 1/12, which equals to 1/2 times 1/6, which equals to the probability of A times the probability of B, these events are independent. That makes sense. They're independent. One doesn't affect the other. Whatever you flip the coin and get shouldn't affect the die roll. So yes, that kind of notion is holding true here with our mathematical definition. Let's look at one more example. The last example I want to look at, a die is rolled twice. Let's let E1 be the event that the sum is a 6, and E2 be the event that the first roll is a 4. Are E1 and E2 independent or dependent of these? That's the question. Well, again, we're going to use that definition of independent events to determine it. And so the probability of E1 intersect E2. Let me quickly write the sample space out first. The sample space, remember, what was that? That was 1/1 all the way up to 1/6, 2/1 all the way up to 2/6, 3/1 all the way up to 3/6, 4/1 all the way up to 4/6, 5/1 all the way up to 5/6, and finally 6/1 all the way up to 6/6. There's 36 outcomes in our sample space. This is the ending bracket here. Okay, the probability of E1 intersect E2, what is that? That's the probability that what we get. We got first row is 4, sum, and sum is 6. That means this is the probability. The first row is 4, and for the sum of the 6, this is 2. This is 1 out of 36. Sum would be 6, the second would be 2. That's second. So what's the probability of E1? Well, that's the probability that, that the sum is 6. Well, how many of our 36 have their sum 6? Well, in this row, there's 1, 5. 2, 4, that's 2 of them. 3, 3. 4, 2. 5, 1, none here. So it's 5 out of 36. The probability of E2, that's the probability that the first row is 4. That's 6 out of 36. 1/6. Note, 1 out of 36, that's the probability of the intersection, does not equal to 5 out of 36 times 1 out of 6. It's not equal to it. But they're not the same. So these events are dependent. And that's the last example I will do. Okay. Thank you very much for your time and patience. And that concludes this video lecture.